Sorry, over chat. This webinar, just to be clear, I'll start with a disclaimer. This webinar is neither sponsored nor endorsed by BEIS, but it has been arranged with their knowledge. It's an opportunity for the authors of the Hy4Heat reports to present their work, which references data, theories, models, and papers created by others, too numerous for them necessarily to be referenced individually. But if you want to find out more information, please look at the reports, which are available and downloadable online at www.hy4heat.info/workpack7 or WP7. The presentations themselves have been ordered to compare the respective journeys of methane and hydrogen molecules as they escape from their confinement in the gas distribution system, how they mix with air to become flammable, and ultimately their conversion into molecules that are the products of combustion. And our goal today is to inform the assessment of relative risk to householders from these mixtures forming and being ignited. So if you think of it as a story being told at a molecular level, then that's a good way to frame this discussion. Please ask questions in the chat, and we'll endeavour to answer as many as we can in the panel sessions. I would ask that you make your questions relevant to the discussion at the time. So if you have a question, for example, on consequences of ignition or the QRA, please wait until the second panel session. So without further ado then, I'll introduce Nick from Steer Energy, who's going to tell you about his leaky pipes.
Right. Good morning, everybody. I'm just setting up for sharing screen. So yeah, thanks for that introduction, Phil. I'm Nick Ryan, Head of Technology at Steer Energy. We carried out the work on lot 1, which was looking at the relative leakage of methane and hydrogen in domestic light commercial systems. So it is essentially, as Phil said, leaky pipes. And I guess the remit we were given was to find a mythical system that leaks in hydrogen but not in methane. And this is an anecdotal system that seemed to be present, but we were never able to find anything. So anyway, the remit was to test a large number of test sections, up to 1,000 test sections. So these involved holes and leaking fittings. So this fitting here on the left here is that's a crimp fitting that's not been done properly. We've done solder fittings that don't have any solder in them, and even legacy items such as this sort of copper sweated into a lead joint here, and then things like compression fittings that have not been done up correctly. So we then carried out tests on flow test regulators. We looked at valves, whether valves would pass at all, and then the relative rates of passing of hydrogen and methane, things like leaking stem seals and the like. And this is a cooker attachment fitting as well. And finally, we looked at damaged sections. So these are the sort of third-party damage that you would see in houses. We've got plasterboard nail through pipes, we've got screws through battens and pipes, we've got burnt components, so in the event of fires, this sort of thing, and then screws into pipes. So it's a very high level look at the results. What we found, a system that does not leak in methane will not leak in hydrogen. So, and when we say leaking, this is relative to the leak tightness tests that are carried out for the relevant standards. So an appreciable leak or a measurable leak using the standard equipment a gas fitter would have. What we did see is that hydrogen will flow more freely than methane. So we've got two flow regimes. We've got here a turbulent flow regime for larger cuts, holes. That's your third party damage where you've drilled into the pipe. Those will leak up to 2.8 times hydrogen to methane. Whereas a smaller leak, such as a leaking fitting, will get a laminar leak regime. For those ones, we're looking at a very, very similar leak rate. But what's interesting is this sort of diagram on the right-hand side, this picture on the right-hand side. So that's a scale view of a 22mm pipe with a 3mm hole in there. So we've got 3 times the volume of hydrogen coming out. And this size is the area in which, if you put a naked flame then that gas will light. So the size for hydrogen, the ignition zone was up to about 60 centimeters away from this 3 millimeter hole, which is quite a large leak in a pipe. Comparatively, methane only 40 centimeters away. So very, very sort of similar, same orders of magnitude for that 3 times the volume. So we looked a little bit deeper into why then, because anecdotally at the start of the work, we were told, yeah, hydrogen's a very small molecule. That's what you'll hear people say. Hydrogen's very leaky. Actually, the size of the hydrogen molecule is, it's 2 hydrogen atoms there, 2 angstroms, essentially, well, 1.8. Methane molecule, you've got a carbon atom with 4 hydrogen atoms. That's 3 angstrom side length. So they are essentially the same sort of order of magnitude of size. So there's no reason to expect that one would leak more than another. And also the size of leaks, you know, the smallest leak that you'll measure using conventional leak testing equipment is about 0.1 millimeter. So that's 10 to the minus 4 meters. These are 10 to the minus 10. So we're talking, you know, 100,000, 300,000 molecules side by side to pass through that leak. So really, there's no molecular reason why, you know, we should see this one leaking more than the other. It is essentially these bulk properties of density and viscosity that mean hydrogen will leak a little bit more. So the theory and the practice that we saw from that, for the larger leaks, it's a turbulent flow response where flow Q there is proportional to the pressure, the driving pressure. So, sorry, proportional to the square root of the driving pressure. So we'd have this non-linear response where hydrogen will flow more than methane. In the case of a small leak, we have this lower part here, Q there, the flow is proportional to the pressure and it's determined by the viscosity. So a very, very similar response between the 2 gases. So just a little look at how we got that information. We're starting here with the gas, which bottle gas we've used, passing through flow measurement and control. So we're measuring flow and pressure, going into the test section, whatever that be, recording that data. For the sample then, for each test, and again, we were testing, you know, hundreds of different fittings and damaged sections. We'd step the pressure up and step up and measure the pressure from flow. So we do that in hydrogen, we do that in methane. For anything like a valve, you know, we do not touch the system in between. So it is the same system that we're testing, or it's close to the same system that we're testing, bearing in mind there will be pressure variations in the atmosphere and temperature variation. So again, those are logged and addressed. So the summary of the results here, and this is the data that is then passed into the other work packs to look at analysis of what it actually, you know, what this means in terms of the actual leakage. This vertical line here to the right of that, these are these big leaks, generally holes drilled. So these are third-party damage that you would certainly know about through smell, likely hear it as well. So these are the things where we really would know about it, we would hope. There, the hydrogen leaks sort of 2 to 3 times the volume of methane. And it's important to say the volume, because if we look at the energy here, the hydrogen energy release is actually less than methane. So these smaller, as we go to smaller leak sizes, we get closer to being a laminar leak structure. This horizontal line here represents the line whereby which standard leak test will not detect that sort of leakage. We're talking seepage and weepage, so it's essentially less than a litre an hour. And there, very much the this could be a leaking system legacy that's been left over from the start of the installation, where perhaps a solder joint was made up but not actually heated up to solder, so it's just the flux holding that in. And these are systems that are found, I wouldn't say regularly, but you know, they're not that uncommon. A compression joint that's not been tightened up or done beyond hand tight after a piece of work done. So these are these sort of small leaks, and really the leakage rate of the 2 gases is very, very, very similar. Just tying in with the theory with a laminar leak, that's 1.2 essentially. So a little bit more volumetric hydrogen. So we're talking 0.38. So, you know, nearly just a third of the, just over a third of the energy. So actually, in that sense, hydrogen will be safer. Hydrogen dissipates quicker as well. So it dissipates in air 4 times quicker than methane. So that actually puts it a lot safer in that context. So I'd move on to a couple of other little bits of work that we have done since then. I think this is we were trying to sort of develop what does it actually mean, and I carried out some tests of ignition, how easy it is to ignite the 2 gases. And we had that little sort of sketch earlier on where I showed the sort of volumetric size of hydrogen and methane through the 3 mm hole. Well, this on the right hand side, this is a 3 mm hole here. We're up to sort of 60 centimeters at the top there. We could ignite the hydrogen from 60 centimeters. The methane, it was igniting from about this distance. Once they're ignited, though, the flame size, in fact, methane flame is generally a little bit larger than the hydrogen one there. So the hydrogen burns with a more stable flame. It is slightly easier to ignite, and you can ignite it from slightly further away, but it's certainly not a case of we've got a 3 mm is a large leak out of a system. Certainly not the case that any spark in that room will light it. You've got to be really quite close to that ignition source for these. Now, it's a different case if the gas builds up in the room, and some of the speakers later today will be talking through those. But what we can see here is the flame size, the energy release size is very similar, even though volumetrically we have more hydrogen than we have methane. We had a variation piece of work on the Hy4Heat project where we looked at as close to a live site as we could. It was a decommissioned boiler house on an MOD site, which was due to be demolished, but we had an opportunity to go in and test the boiler house in methane and in hydrogen. So one of the learnings we took from that, the sort of high level result, was that we had very similar performance. The system was a good system. It did not leak. So it essentially did not leak in methane. It did not leak in hydrogen. So again, that ground truth, the work that we'd done to date. But the other thing was it was incredibly difficult to test the same system twice, because to remove one gas and replace it with another, you had to break the system. We had to open up vent ports. We had to cycle valves to test whether the valves were passing. So you can never really test the same system twice, but essentially it was a good system in both gases, and would certainly have passed leak tests. So one other thing we've been looked at, we had another variation to look at purging. So this is the process by which we commission a system. So it starts off in air and you would then transfer into fuel gas. Now, the density, these bulk properties of the hydrogen, the fear is that hydrogen will stratify in a pipe, which we did not see happening and have not seen happening yet. It would tend to rise to the top of a pipe. But when we purge, now these purges have been carried out much slower speeds than would be recommended in standards, because we're essentially trying to experiment to see where the purge system stops working. We start getting this situation where hydrogen will bypass or methane will bypass the air. And really, we did not see that happening. And in fact, if we look at this one, this is controlled by a 2 mm nozzle here. The hydrogen in blue, the methane is in the orange with the tick marks. And what we actually see is the hydrogen actually purges better than methane. Now, part of that is the faster flow speed. As hydrogen starts to go through the system, this is being controlled by a purge nozzle, so that we know that hydrogen will flow more freely out of the nozzle, out of the hole, so then the speed increases and we get a better purge like that. Also, I think the increased coefficient of dispersion helps as well. Hydrogen wants to mix with the air more, so we don't get those pockets left behind. So that sort of summarizes where we got to. I think it's probably worthwhile just going back to that summary of results slide there, which I know will lead on to some of the other work. And really it is, we did see more leakage in hydrogen, but it does follow the theory. You would expect 2.8 times the leakage in hydrogen compared to methane for larger leaks, and this 1.2 times here for smaller leaks. So there will be situations where a gas system is on the edge of passing a leak tightness test and it just passes in methane and it will not pass in hydrogen, it will fail in hydrogen. So if those same leak test criteria are used, the hydrogen systems will be more safe. I would say, though, those sort of systems that are on the edge are likely to be detected through smell, because the odorization, it will detect really, really very small leaks, as long as it's not in a well-ventilated area. And if it is in a well-ventilated area, then the risk is a lot lower as well. So anyway, that sort of concludes my part of the presentation. I'll stop sharing and hand over to the hand back to Phil.
Thanks, Nick. Very helpful. And we're now going to move on from leaks in pipes in controlled circumstances to a more real-world view of what causes those leaks, how frequently they happen, and what scale they occur at. And that's based on some real data. So a nice comparison there. So over to Paul then.
Okay, thanks, Phil. I'll just start sharing my screen. Okay, so this is the area of work that we looked at in terms of gas escapes and the frequencies and magnitudes that we would expect to happen with natural gas, and then comparing it to hydrogen. And there's a reason that, a number of reasons that we decided to use it in this way, really. The starting points for this are essentially the observation and the fact that gas escapes occur with natural gas systems today. They are different sorts, some obviously large, some small, and in between. Because we're looking at, with Hy4Heat particularly, we're looking at domestic properties in the main, we're looking at things downstream of the emergency control valve in your house, we're looking at distribution temperatures and pressures, so low pressures within the tens of millibars generally, and ambient temperatures. The corrosion mechanisms which people worry about for high pressure hydrogen embrittlement or for high temperature hydrogen attack, for example, they don't occur in the same way. So the principles that we're looking at is that the type of gas that's being conveyed is going to be independent on the development of escapes. So if that's the case, then we draw the observation that by understanding the nature of the escapes that occur today, by understanding the fluid dynamics and the physics and the observations from the experiments which Nick has just described there, we can understand what would happen for a similar system, similar failure mode, if hydrogen was to be used instead of natural gas. The first step was to look at what's out there in terms of literature. There's limited information there, so we are able to look back for some of the old data, some more recent, and then some things that we had to get specifically asked. So the first bit we looked at was King report, as it's called, which was carried out in the 1970s as a consequence of the conversion from town gas to natural gas. So when this happened, there was a perception that there were as an increase potentially in the number of explosions that were happening. So the government wanted to find out whether this was the case. So they looked into this, they did various statistical analyses and concluded that there was no difference in the fire and explosion risks and consequences between town gas and natural gas. And what we thought is it's a good point to start from there, because if you're not familiar with it, town gas was a mixture of gases produced by chemically treating either coal or latterly oil, and it's predominantly carbon monoxide and hydrogen in there. So there was no difference in the fires and explosion consequences that were arising there, but there was a reduction in carbon monoxide poisonings because you didn't have the carbon monoxide that was previously used. So we looked again at more recent data, because obviously time moves on, that's quite far removed. So the HSE publishes various different reports. So the RIDOR regulations, which require reporting of incidents, have got specific features under the gas safety management regulations where gas incidents have to be reported, even if they're not at a workplace per se. So these are reported as filed under what they call RID gas. The thing we've got to be careful with this is that RID gas includes both natural gas and also bottled LPG. So there's cylinders of gas that you can see sometimes that people have got. The problem with that is that although gas safe fitters are required to work on natural gas systems, the LPG is a lot more DIY tended to be operated. So you have regulators that people fit themselves, they have Jubilee clips, and they have rubber hoses which may be of any variety of ages. So looking at failure modes and so on with natural gas, which is buoyant, and LPG, which is heavier than air, can potentially mislead you. So what we wanted to do was to find out further detail. And this we found from Freedom of Information Act request to the Health and Safety Executive to find out more about their internal reports, specifically about natural gas and excluding bottled LPG, which we've looked at over a number of years. These are reported on gas years, so it's like a middle of the year to middle of year calendar that's used conventionally. And we've got there's variation year on year, but in these 3 periods there's about 260 GSMR reportable incidents per year. Of those 260 incidents, about just under 20 incidents per year result in injuries. So about 7% of those incidents result in injuries. So again, it's worth noting that it's working well as a kind of leading indicator in that there are incidents reported more than are actually inherently resulting in injuries. And that's what we've got to make sure is that if there is any conclusions about changing to hydrogen, that's got to be at least as safe as we are now. So where are the knowledge gaps? What do we actually need to know to understand what's happening? So first off, we need to have details of the RIDDOR events beyond the one-line summary of what's in there. As you can imagine, when people are responding to gas emergencies, their top priority is not filling out the description there, it's making the system safe and so on. So we need to try and get a bit more detail if possible. And then also the question, what happens when there are gas escapes which don't cause a RIDDOR reportable event? So if you've got a leaking gas pipe that's got a sense that you can smell gas, but it's not building up to dangerous levels, then that's not going to be RIDDOR reportable, but obviously it is still an escape which is happening. So the scale and the magnitude of these things, again, is worth getting to understand here. So there are about 24 million gas meters across the UK now. And from those 24 million, there's about 400,000 incidents and calls that people have to respond to per year, which is it's a large number in itself. But if you look at it there, essentially it's saying that about 1 in every 60 years per meter point, there's going to be an incident that's responded to. And then from those 400,000 down to 260 is several orders of magnitude reduction. So the people do respond and investigate these incidents and make them safe in the vast majority of times. So it's understanding what is happening along those steps that's leading to the risk reduction. The gas industry, they use the first call operatives, the FCOs. These are the gas fitters, engineers working for the gas companies who are trained to respond to the emergencies. And they're the experts, they know what's happening. And we wanted to get additional information from them from incidents as they were called out. This shows then how we sort of set out to look at it. So essentially 4 steps from designing the experiment of finding out what we wanted to have. So looking at a series of questions that we could ask the FCOs to respond to during an incident, which wasn't going to impact on their timeliness. And that's really an important factor there, is if we're going to ask people for data, it's got to be something they can answer simply. It's got to be something that's in a black and white straight area if possible, rather than free text, because that's possible or very difficult to process automatically. And then looking at the sample size. So we've set out ourselves that, obviously we'd have liked to get as many as possible, but we set a target of about 1,000 incidents that we wanted to have looked at in the minimum. So we developed this. We developed an app that they could pretty easily use to fill the data in, so there was no data entry, transfer from paper, etc. This then was deployed, so the FCOs were trained in their depots to make sure that they knew what to do. They weren't asking people to go out and use the system they weren't familiar with and run the risk that they didn't know what to enter on it. And started with one area before rolling out to 2 other locations, and importantly, rolling out across the country. So it wasn't just finding out about gas incidents within one particular geographic area, which might have some sort of local foible to it. So this was carried out over a period of a few months with regular updates, with a dashboard of results. And then finally, the key point then was to take that data which had been looked at, take the results and say, well, what does that mean? What does that show us and how can we make use of that? And that's the point then where we used a lot of NICS results as well. So I've just got a couple of shots here. So you can see there's the screenshots from the data collection app on the left, again, made to be as straightforward as possible because the FCOs have got to prioritize their safety aspects of their work. This is, this is important info that we felt, but making sure people are safe is always going to be the top priority. And then the graph on the right was showing towards the end, or at the end of the sort of the period that we had, where we'd got the incident investigations, so showing that we had about 1,000 in total, or more than 1,000 in total. The stretch goal of 1,000 per GDNO was very much a stretch goal, so we weren't setting that as the thing we had to have. So all of this essentially was there were 1,300 call outs. Of those, about 1,100 were gas escapes, and as we'll mention later on, of those gas escapes, about 900 were within the scope of Hy4Heat, because again, reiterating the point meant before, this is looking at things after gas meters essentially. So what did we see from this? We've got a couple of slides with sort of breakdown of the data, and you can have a look at the full data in the reports on the Hy4Heat website, which I put the link in the chat beforehand. We found there's sort of a number of sort of big hitters, as it were, gas meter installations. A lot of leaks were associated with those, with gas meters and regulators is the point where sort of quite a lot of those escapes happened. We've got pipeworks, we've got fittings and the pipework itself. Going there, obviously more escapes from fittings rather than just corrosion on pipes, because there's not a huge amount of mechanism that a pipe by itself will spontaneously corrode. There's more third-party damage to those. And then importantly is understanding with the appliances where they come from. And the largest number of reports for these were hobs, and that's, I think, it's quite understandable, because when you're using a gas hob, you are close to it, and also they've got a lot of valves and knobs on them, which have got potential for leak up valve stems, for example. And boilers are also large there, because most houses have got a boiler when they're on gas. We compared this to historical data. We compared those locations and noticed that, again, both the FCO data that we had carried out and the RID gas data showed that there was an increased number of gas escapes from meter installation areas than in the sort of the older version in the 1970s. The conclusion from this is one which I think is already well known by Health and Safety Executive and others, that the rate at which smart meters have been installed means that there are more joints being broken and remade than there would have been in the longer history. So that's why there is an increase at the moment. And again, these are call outs which aren't necessarily leading to incidents. Remember, that's the key, is the safety is still there. This, I'm not going to go through all the numbers on here. This is showing how we then segmented the results. We're looking at escape mechanisms, whether it's from regulator failures, test points that have been left open, leak along threads, and so on, and where they happened. The table on the right, on the other hand, shows the cause, the way by which it happens. So whether it's third party, somebody taking a meter out and leaving uncapped, or putting a nail through a line, for example, different sections there. And what we did with this was we took these data at these points, and we sort of attributed then a leak rate that was consistent with the data which Steer Energy had carried out. So looking at a dry joint, what kind of leak rates you might expect to have from that, the holes that you would have in there, what the leak rates were. And in many cases, especially the larger holes, these are, these match up just exactly as you'd expect from theory. There's nothing in there which is going to give you unusual fluid mechanical properties. And these then we were able to sort of across the the 900 releases within the houses that were within scope attribute a rate with natural gas and attribute a rate with hydrogen. And this is the sort of the S curve of the cumulative count. The vast majority of the release rates were very small, with larger ones going up. And they've got a sort of point again, the sort of the 0.001 meter cube per hour. The liter per hour is the point where you've got the liquid pass the tightness test, as it were, and above that increasing rates. And of course, as we mentioned before, always the hydrogen is going to have a higher release rate volumetrically than natural gas, with the larger difference at large rates where you're turbulent, but the energy release rate is lower or comparable with hydrogen compared to natural gas when you look at energy rates. So what do we actually conclude from this? Well, the conclusion is a set of S curves and data that we are able to use in the building up the quantitative risk assessment in terms of the types of, if there is a hole, what is the release rate going to be, and so on. And the QRA is a section of discussion later on. So of the 1,300 surveys, we mentioned there about 900 were downstream of the emergency control valve, and thus in scope for Hy4Heat's work pack 7. Most escapes would have been below MPLR on natural gas, and some of them would have been above the MPLR on hydrogen. So although that's that difference there, there's the increase there, because the MPLR is set at a low level, it wouldn't create a flammable atmosphere with either natural gas or hydrogen in those cases. A small number of escapes, so about 3% of them would give rise to flammable atmospheres if you had either natural gas or hydrogen, and if you allowed them to continue indefinitely. And that's the key as well, as when we're looking at this, is making sure that we understand what happens in terms of dispersion and times of response and so on. Spontaneous large escapes are extremely uncommon. Pipes don't just disappear. Pipes don't suddenly develop a great big hole in there, certainly not with the temperatures, pressures and materials that we have in gas systems that are used today. So it's generally gradual over time if it's something which is happening by itself. So corrosion, which is gradually getting worse, or a joint which is gradually drying out. And odorization then works as a detective mechanism, again, because the smell of the gas builds up and is at a noticeable level before you are releasing dangerous amounts. The most significant escapes, the largest ones, can be well mitigated using excess flow valves, where if you have a very large flow of gas, an excess flow valve is a straightforward mechanical piece of equipment which could be put into the pipe and will act like a fuse or like a miniature circuit breaker that you've got in your electric system to stop the gas flowing any further. And then finally, the point I mentioned before, that a large proportion of these escapes are associated with meters, and this is a known consequence there. Okay, so that's my set of slides there. So thanks, and I'll pass you back to Phil again.
Thanks, Paul. Full reality check there on what causes leaks, how often they're caused, how large they are, to compare with Nick's studies on how gases leak from pipes. We're now going to go on to Georgina's presentation, where she presents the findings of, once those gases have leaked out of pipes, what happens to them in the atmosphere within the building. So I'll hand over to George now.
Morning, thank you very much. I will just share my screen. Hopefully you can see that. So I'm going to be looking at gas dispersion, following on from sort of the initiation of a leak, as the guys have spoken about so far. This is going to be sort of a snapshot of the work that we've been doing. This is based on over 300 different experiments that have been carried out over a range of different projects. And I'm going to be looking at an overview, basically, of gas and air concentrations that are reached after a leak, the pattern of dispersion of both hydrogen and methane in a domestic setting, the gas inventory that you get after this, the effect of ventilation on these concentrations, and then just a summary of the key findings of this work. So the primary risk from any flammable gas ignition is an ignition of a gas and air mixture, and this applies to both hydrogen and methane. Studies have shown that the greatest risk of sort of damaging deflagration tends to correlate with higher concentrations, and particularly near stoichiometric concentrations of both hydrogen and methane. So if we are to understand the risk associated with using hydrogen in a domestic environment, it's important to understand how it actually moves around a property if it does leak, how high these concentrations may get, and most importantly, kind of how this compares to the situation that we've got at the moment with natural gas, because we do have a flammable gas being piped into our homes at the moment. I should just mention that this focuses on the dispersion of gas. It doesn't consider the consequences of ignition, and that is discussed later, some of the presentations that are following later on this morning. The previous presentations have sort of detailed that gas leaks are rare, and certainly the majority of gas escapes within a domestic setting are small. However, if you do get a larger gas escape, this can lead to a risk, and this is what we want to try and understand. So data from several experimental studies have been looked at. That includes Hy4Heat, Hy4Heat, and H100. And we've used the data collected under these studies to understand the following key aspects. So the pattern of gas dispersion following a gas escape in a domestic environment, the impact of the escape location on dispersion patterns and the gas in air that's seen in that environment, potential areas of gas accumulation. This links potentially to meters that were mentioned earlier in terms of if you get a leak from a meter in a cupboard. And then the impact of ventilation on these, and that includes house properties as well as additional ventilation within the space. So most of the experimental data was collected from these two properties. The first was collected by Kiwa under the Hy4Heat project, and the second collected by DMVGL under the Hy4Heat program. One is an old cottage, that's on the left-hand side, and this was in Scotland, in a deserted area, built in the 1800s of solid stone, rendered. This was actually sealed up in terms of air tightness over the duration of the experiments to understand the impact of air permeability on the gas dispersion that we saw in that property. So we had a number of experiments that were repeated at different levels of air tightness to understand that impact. The other property is a new build, built roughly 2019. Both properties were fully unfurnished, but were sort of finished. So they had second fit, but they didn't have any furniture within them. So gas was injected into these houses at known and controlled rates, and that was dependent on the leak scenario that was being simulated. We were trying to simulate sort of potentially common activities such as a leak in fitting or a leak from a gas pipe, or maybe a DIY incident where you'd put a nail through a pipe or something like that. But we also wanted to simulate larger leaks, such as perhaps a mains failure. So we had a wide range of leak rates into these properties. The environment within the house was actually sampled in lots of different locations. So in every room for the Hy4Heat project, and then in every room plus other areas such as voids and wall cavities under the Hy4Heat program. And this was sampled at low, mid and high levels in each of the rooms. The environmental data was collected throughout the experiment, and from this, key parameters could be determined from each of those sample points, such as the maximum gas and air concentration that was observed in each of those sample points, and that could lead on to then understanding the gas inventory using those collected numbers. So this figure shows the results of all of the test data for both methane and hydrogen through all of the experiments. This includes Hy4Heat, and H100. It's expressed on a kilowatt basis, and that allows for comparison between the gases. As Nick mentioned earlier, flow rates are different between the gases for the same energy rating. The values that are shown here are actually the maximum gas in air concentration that was recorded in the room of gas release. A lot of the releases took place in a kitchen. That was to sort of simulate, that's sort of an area where you may consider that you've got a lot of gas appliances. Obviously, you've got a cooker in a kitchen, that could potentially be gas. Boilers are often located in a kitchen. And we also looked at kitchen cupboards in case you had pipe runs through cupboards or meters perhaps within a kitchen space. In all instances, this maximum value was actually recorded at the ceiling, and we will touch on this a bit later on. As you can see, the data is fairly complicated. As well as comparison between the gases, you can see that there are lots of different factors that actually affect the results of the concentration at the same release rate. That includes things such as whether doors, internal doors were left open or closed. It also shows the importance of air tightness of the property. So how leaky is the house? How easy is it for any escaped gas within that house to escape? One of the key points, however, to note is that Nick mentioned earlier on that you do get, or you would expect approximately 3 times the volumetric flow rate of hydrogen compared to methane at the same energy rating. However, when you're actually looking at the maximum concentrations that you observe, you may think you would get 3 times the concentration, but you don't. You actually get very comparable concentrations between methane and hydrogen when you're leaking at the same energy rate. I've broken this down into escapes by room. This is to try and sort of clarify some of the data because the last graph was, quite busy. Again, we're looking at a comparison between methane and hydrogen. So hydrogen is on the left, methane is on the right. When you're looking at low energy releases, as you may sort of expect more commonly, sort of below the 50 kilowatt rating, you can see that concentrations are very similar for the two gases. And the variations within the gas itself tend to be because of different environments that they are being released into. So you can see high house 1, 2, and 3 is basically changing air permeability of the property. So as the property increases in air tightness, you tend to get slightly higher concentrations. And also looking at doors being opened or closed. At the basement at the Hy4Heat project, again, that has an impact on the maximum concentration of gas that you see within that space. Now, I mentioned earlier that the maximum concentrations were seen at the top of the space, and so far we've only sort of looked at the maximum concentrations that have been measured in these experiments. Now, one of the key findings of the work was that when the gas was released at low pressure into a naturally ventilated space, both hydrogen and methane tend to stratify. This means that you get the highest concentrations at the top of the room and comparably very low concentrations at low level. Now, the height of gas release has a direct impact on this. The higher your leak, we tended to see the higher concentration at the top of the space. This is all due to the buoyancy of the gas. Hydrogen is very light, so when it is released into air, it tends to rise. It will always rise to the highest space. And this creates this sort of layering effect within a room. Now, I've tried to demonstrate the stratification in these graphs. This slide demonstrates tests taken from the Hy4Heat project. Each group of 3 bars represents a single test. And each bar is a different sampling height in the room. So the blue bar is the concentration at the top of the space. The orange bar is the concentration that was measured in the middle of the space. And the grey bar is the concentration that was measured just above floor level. This also sort of shows the effect of air permeability on those concentrations reached. Each pair of tests is the same test release rate, but done at a greater level of air permeability on the second test. So you can see sort of two factors here. You can see that the stratification is very clear. You get much higher concentrations at the top than you do at the bottom. And you can also see that as you increase the air tightness of the house, the maximum concentrations that you see at each of those levels also tends to increase. And this is the same for both hydrogen and methane across those tests. So we're now moving on to look at gas inventory. This is sort of part of the picture when considering the amount of energy and potential damage that could be caused in the event of an ignition. This will be talked on a bit more later, so I won't go into detail about that at the moment. We used the maximum gas and air concentrations recorded in each test to work out the inventory in the properties. Now, this was done on a whole property basis, but it can also be done for individual rooms and even taken down to individual cupboards, for example, to understand how much gas was in each enclosure that we were measuring. In all of the test work that we completed, methane actually resulted in higher gas inventories than hydrogen at the end of the test periods. So similar to the first graph that I showed you about concentration, this graph shows the whole house gas inventory for each of the tests. This is split for methane and hydrogen. So the methane is the orange shapes, hydrogen is the green. The symbols represent the scenario. For example, it shows the difference if the release took place into a room, whether it took place into a cupboard, or whether it took place into a basement. Again, it's fairly complicated. It shows a wide spread of results for similar escape rates, and that demonstrates, again, quite clearly how other factors, such as available ventilation, even whether it was a windy day, has an effect on the amount of gas that is seen in a property after a release. For both hydrogen and methane, the gas inventory calculated for the basement is higher than any other scenario. That is probably due to the reduced ventilation active in this environment. And again, that sort of supports the theory of other environmental factors being important in terms of the amount of gas that you get after an escape. But as I said, overall, the total house inventory was lower for hydrogen than for natural gas. So we've mentioned ventilation. This figure sort of shows the impact or beginning to understand the impact of ventilation just through the simple practice of just opening and closing internal doors when a leak is taking place within the property. This is looking at maximum concentrations observed in a kitchen and in a basement when the kitchen door was open or closed and when the basement door was open or closed. The escape in the kitchen was actually in a cupboard. So this was an escape in a cupboard that was released into the kitchen and the resulting concentration from that. The solid shapes show the door closed and the hollow shapes are the same scenario, but with the door open. And you can see that in each scenario, the maximum concentration within the room is reduced by about sort of 5 to 10% when doors are open compared to doors being closed. So that sort of begins to show the effect of that increased ventilation on gas concentrations within that space. If we move on to look at if that ventilation is to the outside, this graph shows the maximum concentrations in the kitchen and in a cupboard when you add ventilation to it. For this experiment, hydrogen was injected into a low-level kitchen cupboard. The orange lines shown here are the concentrations within the cupboard. So this is the maximum concentration that was in the cupboard itself, so a small enclosure. The blue lines are the maximum kitchen concentrations measured during the test. I should sort of say here that these flow rates were quite high This experiment was not to sort of demonstrate a very particular test. It was to demonstrate the sort of effect of ventilation and chosen to show the venting effects, not necessarily a likely leak scenario. But it does clearly show the effect that having a vent produces. So the lines on the left-hand side are with no vents present at all. The lines in the middle include a small size vent, and then the one on the far right is a 200 centimeter squared vent within that space, and that's ducted to outside. And you can see the effect that has on the maximum concentrations that are experienced in those spaces. So sort of summarizing the key findings, I suppose fairly obviously, the higher release rate you get, the higher gas in air concentration you're likely to see within that space. You tend to get comparable maximum concentrations recorded for hydrogen and methane for the same energy release rate. The total house inventory at the end of the test period was actually lower when injecting hydrogen compared to methane. The height and location of gas has a marked effect on the maximum concentration that you are observing in the space. Gas escapes in a cupboard can result in high concentrations, and basement releases can also result in high concentrations in inventory. The air permeability of a property has a huge influence on the gas and air concentrations that you see, and sort of adding to that, the effect of ventilation is strong. So there is a strong effect of adding ventilation to a space in terms of taking gas concentrations down. And as has been mentioned by the two previous presenters, if you reduce the risk of increasing gas flow into a property, you can do that by adding an excess flow valve. And that is an option for reducing risk, or the risk of large escapes occurring within a property. So that's it for me. Hopefully that was a sort of an overview of a fairly complicated subject, and I will hand back.
Thanks, Georgina. Now let's enter into the panel discussion. I've just realised I've made a monumental error on the chat. My last comment was to divide gas and air concentrations by 10,000 to get parts per million. I should have said multiply rather than divide, obviously. So apologies for that. I've been trying to answer questions as they come up, if they're relatively quick and simple to answer, but we do have a couple that are that are now in the Q&A. So again, apologies for my unfamiliarity on Zoom, but thank you for using the Q&A, because it means we can track those answers. Before we get into the ones on the Q&A, though, there was one, or rather two, on hydrogen embrittlement and temperature, and in particular, let me get the question exactly right. Where is it now? How can we discount hydrogen embrittlement in appliances such as fires or boilers when the burners will be well above 500 degrees and localized equipments will be well above ambient? If we deal with hydrogen embrittlement first, which is a separate phenomenon to sensitivity to flame, to temperature, then if I can pose that one to Paul, could you answer that one?
Yeah, and basically hydrogen embrittlement is something which happens at much more elevated pressures, so tens to hundreds of bar of pressures where it's concerned. So if you're dealing with transmission pressure pipeline pressures, then that's something which is an area of concern, and making sure and understanding that the steels that are used are compatible there. At low pressures, so the 21 millibar type, or even any of the local distribution pressures, hydrogen embrittlement isn't a phenomenon which can happen there. High temperature attack happens when you've got primarily it's a dry hydrogen that's at high temperature breaking down into hydrogen atoms, which then react with carbon within steel and cause it to become damaged that way, which is essentially when you've got the flame, you are very quickly destroying the hydrogen. So the hydrogen is very reactive with the air. So I think it's one of the bits which you want to make sure that your pipe and your metal is not too hot, just as a general a general design basis. But it's not fundamentally a hydrogen thing with the conditions that we have within appliances.
Yeah, it's one of the reasons why we need to develop appliances that are specific to 100% hydrogen. But it's an engineering challenge. It's not unachievable, as has been demonstrated by Hy4Heat. The next question then is the first one in the Q&A, which is, I understand you have similar energy with a leak of natural gas and hydrogen, but does the hydrogen then light more easily? And Nick, if you could answer that one, please.
Yeah, certainly. We did find it easier to light the hydrogen, but not excessively so. And this was just, it was tests we were doing ourselves. I think there's going to be more discussion in hydrogen ignition in the later part of the panel discussion. But for our test, yes, you could light the hydrogen more easily, but not excessively so. So it was maybe sort of distance away from the plume or the leak, to say for, you know, if the it was about 2/3 of the distance methane, and then a hydrogen would be, so yeah, 1.4 or 1.3 times away, and you really had to be on top of that plume. You know, if I put the light just to the side of the plume, then it wasn't happening. So yes, you could light hydrogen a little bit a bit easier. It would, the flame speed was quicker as well, so it would go with a bit more of a woomph, but then the flame is a lot more stable once it's there.
Thanks, Nick. For another question, I see I've had two people ask about energy release post-combustion now and the consequences of that. That's going to be dealt with in the second half of the presentation. I know it's the more exciting bit, but please have some patience and we'll deal with that in the second panel discussion, which Mark Crowther will moderate. Until then, I've got one remaining question on what size of leak triggers the excess flow valve in the meter. Now, I know that Paul has done a fair bit of work with on Work Pack 10, which is the development of hydrogen meters, and so I'll let him answer that question.
Yeah, so we've got two excess flow valves that are primarily there. First off, as a excess flow valve that's of the conventional sort, something which goes into the pipeline, and you have the spring on there which keeps it open during normal flow, and when you've got too much flow, it closes it. That's the ones that you get basically are generally rated to be about 20 cubic meters per hour for hydrogen. That's where we're looking at, because that's essentially the energy flow rate. That is the maximum flow that a meter should be giving into a normal size house. Within the meter itself, and it's more of one of the other parts of Hy4Heat rather than Work Pack 7, but as has been asked here, the development of the gas meters for hydrogen includes the excess flow valve, excess flow functionality, where it monitors the flow, and there are a couple of bits that it looks at. If it goes above the maximum rating of the meter, then that's a trigger to close the supply because that's too much flow. Also, if there is a sustained flow above a value which can be set. And what we're looking at is that this is something that would be configured during installation and commissioning of the gas system. So when you have meters, when you have your meter set up, when you have a boiler installed and whatever other appliances there, the rate of gas that you would expect to have during normal operations if they were working together would be configured onto there, so that essentially if you ever reach above a sort of small threshold above those maximum rates there, that would operate the excess flow functionality of the meter itself. So that's additional stuff which they don't do today.
Yeah, it's interesting to note that the current standard for excess flow valves is a test of, I think, 3 to 4 times the design flow rate is the test flow rate for when it should operate. We consider that to be way too high for our purposes and for the use of an excess flow valve, and so that is a piece of work that we're hoping to look at soon.
I could just add, in the question was about hole size as well. If we take, say, for a standard domestic, if you take at the moment the regulator rated to 6.4 meters cubed per hour, just over 6 meters cubed an hour, that would equate to a 7 millimeter hole size would deliver that. But you know, as Paul's just said, actually going forward, you'd want to actually drop that 6 meters cubed an hour for individual installation, so it would then be a smaller hole. And I think the sort of energy releases that Georgina was talking about in her presentation, when we're talking 300 kilowatts, that's a massive, you know, that would have been picked up far before, you know, as soon as the release happened. I think it wouldn't run for any length of time.
Okay, I think we have a couple of questions on consequences, and one which I don't fully understand on voltage breakdown of hydrogen at stoichiometric. I think that's post-combustion as well. So we'll park that for the second panel discussion. And if the person who asked that could perhaps add something to that to perhaps explain that a bit more fully, I think that would help the second panel. Let's now move on to the second session, where I think Nicole's going to start on the literature review of consequences. Thank you, first panelists and presenters.
It's great, thank you. I've just unmuted myself. Good morning, everyone. I will try and share my screen. Let's see if that works. Sorry, bear with. I'm working from a laptop here, so it's a little bit tricky. George? Right, sorry. Aha. Fantastic. Can people see that?
We can.
Brilliant. Okay. Technology, don't you love it? Right. So from the presenters this morning, you have already heard about the likelihood of a leak occurring and the sort of concentrations that will build up when that happens. So I'd like to talk to you about the see, my slides have gone out of order a little bit here, but the what actually happens should an ignition occur. So the items we'll cover in the next 15 minutes or so. I'll give you a little introduction to the work we did, explain the methodology that we carried out, which was predominantly a literature review of existing data, the extraction of data where we could, some processing, and then talk through some of the key findings, which included ISO damage curves, sort of how consequence varied with concentration, obstruction and venting of the enclosure in which it took place. So as my colleague Georgina already said, the primary risk to any from any flammable gas is its ignition in air as a mixture, which applies to both methane and hydrogen. So we needed to understand the likelihood of a leak occurring, the type of concentration that would be achieved, and then see what would happen if those sorts of concentrations were ignited. And that's what my presentation will deal with. So the first stage was to look at data that existed, and sort of for obvious reasons, there's not a lot of data on real ignitions in domestic premises. So you have to look at what does exist. So we looked at over 14 or about 14 experimental studies that involved ignitions of gas within enclosures. These were from around the world: European studies, US studies, and Japanese studies, and from a wide timeline from the early 1900s to present day. We looked at academic reports, industry papers, from contacts we had, and various experimental studies. Each piece of paper or report was thoroughly reviewed. We summarized the findings, and we sort of assessed the each one in its context and relevance to a domestic situation. We extracted key data from each report and assessed looked in detail at the context and the setup in which the experiment was carried out. What was it trying to achieve? We looked at the findings of the work and observations, and we paid particular attention to any evidence of detonation where it could be found. Detonation obviously is not something you want to occur, and it is very important when it comes to assessing consequence. We took overpressure data from any of the reports where we could find it. Most often when an experiment involving a flammable gas ignition is done, pressure is measured using high-speed pressure transducers. So we were very keen to try and find any sort of quantitative information we could on that. We also took some of the pressure traces that we found, particularly on the older reports, were a little bit blurry, a bit hazy, and we digitized them and were able to extract maximum overpressures and impulse data from these pressure traces. Impulse is the area under the pressure transient, so it's the integral of pressure with respect to time. We were then able to plot data from several different experiments on what we call ISO damage charts. And this is an example of a ISO damage chart, which shows pressure along the x-axis and impulse along the y-axis. The black curves show thresholds for where low and mid and high damage to structural components occurs, and the colored lines represent glass breakage. So you can see sections of the graph where damage may or may not occur. These charts were derived from real observations of real damage to buildings, including damage from bombs during the Second World War. We obviously had a lot of data, so we split the graphs down into concentration bands to allow ease of visualization, basically. And we chose bands that we thought we had a feeling that initially hydrogen, from between about 0 to 10%, hydrogen would be less than methane in terms of consequence. There may be comparable damage from between 10 and 15, and 15% upwards, hydrogen is likely to be more severe. And in which case, this is where we believe that preventative measures would have to be put into place to avoid these sort of concentrations. It should be stressed that the sort of consequences that would from the above bands are very subjective. They're subjective to experimental conditions and may vary. So we plotted ISO damage curves for each such band. Here's an example of the first band, which is a 0 to 10% gas in air concentration. You'll see that we have hydrogen results on the left and methane results on the right. We have we did, after discussion and consideration of the experiments, we just, you know, this point on the right on the hydrogen graph was sort of decided as not relevant or not representative of a domestic situation. It was a shock tube with a very specifically designed insert to accelerate flame front. So you can see generally the hydrogen results tend to be towards the left of the graph, whereas the methane results are spread out a little further. At the 10 to 15% concentration, we have a sort of similar set of results between the two, as in, i.e. they lie in roughly the same area. There again, we discounted the shock tube with the insert as being not representative. The two arrows there show the results of the fire investigation box that we as Kiwa did. At 15 to 20% gas and air concentration, it's all hydrogen results. There were no methane results with which to compare. This could be that in the sort of experimental conditions that we were looking at, concentration above stoichiometric of methane just simply wouldn't ignite. So the same applies to the 20 to 25% gas and air concentration. You can see the hydrogen results are getting, you know, more severe, and they lie towards the higher end of the top right of the graph. And above 25%, there's potentially some significant damage. So some of the key findings from the literature review were that we found some fundamental properties of hydrogen. It has a wider range of flammability than methane. The limits of hydrogen flammability do depend on the direction of propagation. It's roughly 4%, but only in an upwards direction, whereas at about 9%, it could be expected to propagate in all directions. Methane has a lower flammability range from about 5 to 15%. The hydrogen has a potential or possibility that it can transition to detonation at a roughly above 18%. Methane can, but it is a lot rarer. Generally, as might be expected, the higher the concentration of flammable gas, the worse the consequence of an ignition. We saw that the methane severity was seen to peak at about stoichiometric concentration of 9.5%, and hydrogen tended to a maximum about 10 to 15 points above stoichiometric. We had limited data on ignition of hydrogen concentrations much above stoichiometric levels. This is an example of a graph showing increasing overpressure with gas concentration. We also found that the room geometry had an impact on the severity of an ignition. As might be expected, fully enclosed structures result in the highest overpressures, tending towards adiabatic pressure rises. These were not considered relevant to a domestic situation, which is likely to have some form of blast relief, be it a window, a door, or other. The environment in which the ignition does have a big impact on the resulting consequence. This could be the shape of the room, whether there's any constrictions in it. Particularly the inclusion of any obstruction or items within the room can affect the severity of an ignition. This is particularly the case for very highly ordered obstruction. I don't know, for example, the things you might find on a chemical plant, that sort of thing. And that was shown by the very specific shock tube insert tests. These weren't considered too relevant to a domestic situation, as this level of highly ordered clutter is unlikely to be found in such a situation. This is a nice example of the pressure trace resulting from two tests done within the same ISO shipping container, which you can see sort of diagrammatically on the left. There's a pipe rack and a bottle basket, so highly ordered, repetitive obstruction, and the trace on the top right is a result with just a bottle basket, and the one below it is with both, and there's a significant increase in peak pressure. This is another example of obstruction or ordering within the room, and this is the CVE test facility at the University of Pisa. It's a glass construction in which you can vary the configuration of the room inside it, and you can see on the right the results of the different configurations. So the triangles in green show the sort of simplest configuration outside the empty room, and up to the configuration 8, which is the orange circles, showing considerable increase in overpressures as you become more disorganized inside there. Blast venting was very important, and this is an area or something through which flammable gases and unburnt gases can escape after an ignition has occurred, and will reduce the maximum overpressure recorded. Generally, the larger the vent area, the lower the overpressure, and almost all domestic situations will have some form of something that will act as blast relief. Oh, sorry, I'll go forward. And there was also evidence that room shape, size, and vent location can have an influence on overpressure. There can be a complex relationship between the three. this graph, this ISO damage result chart shows the influence of venting. I don't know if it's a bit faint, but the orange squares represent tests done in exactly the same room at exactly the same concentration of 18%, but the ones on the left have a large opening and the ones on the right have a small opening. So you can see it makes quite a big difference. We also looked at glass throw, and we put the results of our fib testing onto some existing data to do with glass throw, and we continue to see a sort of almost linear relationship between overpressure and distance that glass travels. Glass windows obviously also act as a form of blast venting, and they will fail. They have a failure pressure, so tend to fail earlier on in a deflagration or an ignition. As I mentioned before, detonation was something we looked at. It's very important. It's difficult to achieve in simple structures. Of the experimental studies that we showed that had to do with hydrogen, we only showed evidence of complete DDT in one. That's detonation transition in one case, and that was only achieved with chemical explosives. There was some suspected localized detonation in 3 of the reports, and these all involved some sort of enclosure within a room where a localized pocket of gas were at a higher concentration than the surroundings was able to accumulate. Cupboards containing leaks, for example, are one such scenario that may be applicable in a domestic situation. Irregular shaped vessels, such as a car engine within a garage, car engine compartment within a garage could also be such an example. And this next graph shows a result of a pressure trace recorded in a garage experiment in which a car was located. And these you can see these very sharp high pressure rises, quite different to the sort of shape around it. And it was theorized that this is evidence of localized detonation. Thank you very much. That completes my presentation.
Thanks, Nicol. That was a gallop through quite a lot of information there.
It was.
And you did really well to keep it to just over 15. So I won't waste any more time. We'll dive straight into Sam's presentation. So we've got time for the panel discussion. Sam's going to talk about modelling of the consequence.
Yep, certainly. Thanks. Let me just share my screen. So if I share this, let's see it. Can you see? Can you see this here?
Not yet.
Not yet.
Okay. How about now?
That's much more promising.
Okay, that's good.
You've got standard PowerPoint view though, so if you wanted to go into the presentation and blow it up a bit.
Okay.
No pun intended.
Yeah. Okay, I think I'm now sharing the wrong screen. Hold on. Let's bring that one over here. Okay. Apologies. I thought I didn't realize I was next in the queue. I don't know, I will share just quickly the okay, there we go. This should be better. Okay, can you see this one? Okay, so yeah, I'm going to whistle through the consequence modeling that I did, which sort of is on the back of the work that Nicol and Georgina did as well. So I'm just going to go through the types of housing topology that we considered, some of the sequence of events that we considered as well, and obviously some scenarios, just a deep dive into dispersion and stratification, and then looking at the estimation of overpressure following obviously a dispersion and an ignition event in a domestic setting, and then just a quick look at some of the outcomes, and then I'll touch on some of the challenges that we had as a project. with the work pack 7. So some of the type of housing topology that we considered was, so we looked at terraced housing, and this is because 30% of the housing in the UK, or 31%, is terraced housing, and we took this housing topology primarily because also a lot of it is subdivided up, and you also have the close proximity of party walls, so you share party walls with your neighbouring properties, and it also meant that we could extend the assessment more easily to detached housing and semi-detached housing. So why is this? So if we just look at these two examples here, we look at the one on the left, which is obviously the Salford Greater Manchester explosion in 2010, which is in a row of terraced housing, and you can see that for this example, that although the event occurred in only one property, we've got it. It does affect or it brings about structural collapse in both the neighbouring properties and actually the neighbouring property but one as for partial collapse. And this is actually comparison. If we compare this to, say, a detached property like the one in the right side here, which is the Haxbury example, you can see that although there's catastrophic damage to the property or domestic setting or the house where the initial dispersion ignition event occurs, you can see that the properties either side, apart from some of the glazing that's been damaged and some damage to the roof, it's still quite superficial, and the main structure is still standing. So the types of consequences that were considered during in this part of the assessment is so we've got our house where we've got our dispersion and then our ignition event occurring, and we looked at sort of the impingement of occupants in a combusting either methane or hydrogen cloud, and then what that would occur, the number of injuries that could occur externally in the urban realm or the street. We looked at primary and tertiary injury. So primary injury is predominantly injury due to exposure to blast overpressure, which is the threshold for primary injuries is actually very high. We're looking at eardrum rupture and lung hemorrhage, which certainly did not dominate the types of injuries that we modelled. And then tertiary injury is injury due to blunt trauma from falling over or being thrown into something. And then we looked at projection of glazing as well. That also represented the impact from debris following an ignition event in the home. And then the main one that actually we found dominated a large amount of the injury levels is looking at structural collapse. So you could argue that this overlaps with tertiary and secondary injury, but we looked at this separately. So this is where the structural integrity of a building is lost, and an occupant is either injured due to part of the structure falling on them or it collapsing around them. And to do this, we had to take some sort of assumption about occupancy levels in the house, and we took a figure of 1.79. So there's a lot of things that go into this, but it mainly comes from the Office of National Statistics for occupancy levels for a property, and then there's some factors that added on, looking at the level of occupancy based on sort of over time, and a week span. And we did the same thing also for looking at the density of people in the public realm. So although this number comes up as somewhat random, it is based on a lot of assumptions, and bearing in mind that we're comparing hydrogen and methane. If we change this, if we change these figures, it does actually affect both methane and hydrogen by the same proportion. And we did some sensitivity studies on this as well, following some comments from the HSE. And then this slide is just simply to highlight that there were some events that we didn't consider in this comparative assessment, because for both hydrogen and methane, the the consequences or the level of consequences and the level injury would be the same. So I take an example of, we have an ignition event that, a leak, and then an ignition event that then starts a cellulosic fire associated with the combustible load in a property. And then, that combustible load quickly becomes the dominant source of energy fueling the fire. And therefore, actually, whether it's methane or hydrogen that starts that initial fire in the property, for both of them, the consequences are pretty much the same. So for this assessment, we considered two types of enclosures. So we looked at sort of a kitchen size enclosure, which is sort of representative of maybe a kitchen in a terraced house that's not open plan. And then we also looked at a larger enclosure as well, which is, the idea here is that to represent a sort of open plan, or the downstairs of an open plan property. So, we can see the difference between these two is that, okay, a smaller enclosure, you'll have a smaller buildup of gas, so the volume is less, but the length of time it takes to get to a certain concentration will be, obviously shorter for a smaller enclosure than it is for a larger enclosure. But we felt that this represented, a good mix for a terraced house. And when it came to the consideration of dispersion and stratification, so Georgina's mentioned this earlier, but there was a series of tests done at DNV GL Spade Adams facility, where they had 4 different properties, and the outcomes or the outputs from this sort of experimental work that fed into the consequence work that I was leading in this area is looking at how gas stratifies in a property, which Georgina has already covered. But we'll just take one example here, is that, I think this is actually on some of the slides that Georgina showed earlier, but what became apparent is that the concentration at mid-height and the concentration at ground floor level or low level was always often was based on was a percentage of the peak concentration at ceiling level, and this stayed fairly constant. So if we increase the peak concentration, which is always going to be at the ceiling level, the concentration at mid-height and also at ground level stayed very similar or stayed the same in relation to the peak concentration. And this was the case for both hydrogen and methane for a particular leak scenario. So this example here is when the leak is located in the basement, which actually in our case led to the highest combustible load in our kitchen or downstairs enclosure, because you sort of have an area leak from the floor. And we took this work, so the consequence modeling, for those of you who've done looked at sort of vented explosion models before, it's very difficult to put in a sort of stratified confined gas layer, where you've got a variation in concentration. So we came up with this equivalent height methodology, which retained that combustible load, but sort of came up with this equivalent volume of gas, but at the peak concentration of methane or hydrogen in the enclosure. And we had to take some under sensitivity studies on this, which was interesting because actually really what dominates the consequence or the explosion strength when it comes to a methane or hydrogen explosion is actually the concentration itself rather than the way it stratifies. So in terms of estimating overpressure, we looked at we're looking at a vented combustible explosion model, whereby you've got your enclosure that fills with your flammable vapor cloud, and you have an ignition source, and the flame front develops from that point. And we used a model from Warwick Fire to look at this. And I suppose one of the things that is difficult, or these empirical, semi-empirical models don't look at is sort of partial eventing effect that occurs as as your overpressure increases, it assumes that your volume stays the same and that your enclosures of your wall, so your kitchen or your downstairs enclosure, remain in place to determine the peak overpressure. And the reason we want to determine peak overpressure is because this is what feeds into determining the consequences in our assessment. So it was important to it's important to consider furniture and obstacles in a domestic setting, and that a lot of thought went into this with some sensitivity studies. It's particularly difficult to try and determine what the effect is of obstacles such as furniture, but the methodology, or the semi-empirical method for determining overpressure from vented explosions, based on the research that the Warwick Fire Group did, uses this methodology of that obstacles increase the flame surface area that's developing in a vented explosion, which increases the reaction rate, which therefore increases the overpressure. And there's a quantitative way to try and estimate this, albeit there's always got to be some caution when doing so. But actually quantitatively estimating consequences is quite challenging, and the reason for this is because whilst we can have some binary determining structural collapse, for example, in a domestic setting, masonry is brittle, and it doesn't sort of yield any ductility, so it's either supporting something or it's not supporting something at all. There's no sort of halfway house here like there is with steel or reinforced concrete. So when we're in our model, we took, for example, we looked at any non-load bearing partitions or members in a property are assumed to have no structural integrity whatsoever. So once you have loss of structural members in a house, so we're looking at party walls and solid brick walls, then we assume that we get collapse of that portion of the house. But actually, in practice, we know that non-structural members do provide some structural integrity, as shown by this example here, and trying to get this into the modelling is quite difficult. But I suppose the outcome, or the end, that actually the modelling that we did is somewhat conservative for both gases. So the outcomes of the consequence assessment are that, this is a summary, 2 summary slides from the report that I picked out here, and the stepwise nature of these graphs. So we're looking at sort of total number of injuries versus the peak concentration in our stratified enclosure, whether it's our kitchen or our sort of open plan downstairs. And you can see that there's a stepwise nature in the total number of injuries. And this is because the injuries due to structural collapse very much dominated the overall number of injuries. And that is why, when we get a step change, that effectively is representing the change between, zero structural collapse or, collapse of 2 party walls, and then assuming that anything that those party walls are supporting also collapses as well. And then you can see for methane here in this graph that it decreases as we get towards the upper flammability limit of methane. But we know so this is very conservative, and we took this decision to do this because once you get above the upper flammability limit, it's difficult to, you could argue that actually you don't get ignition. Well, we know in practice that actually injuries, when we're looking at natural gas, a number of injuries does actually increase. But given that this is a comparative assessment between hydrogen and methane, it's conservative to underestimate, I suppose, the consequences of natural gas or methane in relation to when comparing it to hydrogen. And then on the graph on the right here is looking at external, or injuries external to a dwelling, and you can see that the number of injuries is much smaller, as would be expected, compared to the total number, because that's dominated by injuries to the occupants. And again, in practice, we can see that actually, the green line is indicative, I should add, but that actually what would happen is that, injuries would increase with increasing concentration of methane, because you're increasing the combustible load that is involved eventually in an event. So some of the challenges that we experienced through this is, as I mentioned earlier, is quantitatively measuring consequence and likelihood, and the dispersion of methane and hydrogen in domestic setting was also a challenge, because we found that we have a large variety in the way that hydrogen methane stratifies, but at the beginning of this project we made an assumption that the buoyancy or the density of these two gases and the difference between them would dominate how they stratify in an enclosure, but actually it is very much down to where the leak is. So if we have our leak in a boiler cupboard and it leaks out the top of the cupboard, in some scenarios you can almost get an identical sort of stratification regime, but that's the same between methane and hydrogen, i.e. a very, very high concentration at ceiling level and virtually nothing at mid and floor level for both these gases. And this is something that Nikhil mentioned earlier, that there's a distinct lack of experimental data, particularly for vented hydrogen explosions, which is understandable. It's very expensive to blow things up. But the models that we used, take into account all of this experimental data, but that doesn't necessarily mean that that's enough experimental data. So I think we highlighted this as in the work that we've based this work on as much as we have or as much as available, but that doesn't necessarily mean that more would not be useful. Lack of detailed knowledge of events leading to past incidents. So a lot of past incidents in domestic settings is based on back calculation. So you've got the consequences, and then a lot of the time it's estimating what were the events that led to the consequences, i.e. how much gas was leaking for how long, is not always known. And then uncertainty and level of accuracy of empirical and computation models is actually less than really needed. And the disadvantage of that in this work is that means that we actually have to be very conservative, in any areas where it's unknown. If things are unknown, then you have to be conservative to take into account that variation in potential results that you could get. So ideally, as you increase accuracy, you can reduce the level of conservatism in your assessment. And I think that's something that we're always going to be seeking going forward. So that's it from me in terms of consequences. I think I've just about kept time. So Phil, I'll hand back to you.
Thanks, Dan. We'll move swiftly on to Sophie then, if you're ready, because I'm conscious we're slightly behind time in total.
Yeah, I'll just share my screen. Cool, so hopefully you can see that. So just kind of following on from Sam, so I'm going to just talk about the kind of what we did kind of overall safety assessment, and in particular with the quantitative part of the risk assessment. So just to kind of recap on the scope.
We can't quite see your screen yet, Sophie.
Oh, you can't see it? Okay. Let me try again. Oh, I didn't click share. Right. Is that working now?
Yeah.
Okay. Okay, yeah, so just to recap on the scope quickly. So we were looking at kind of everything inside of the property. So the cutoff point that we took was the emergency control valve. at the meter installation. So basically everything downstream of that was included in the assessment. That includes the meter installation of the internal pipework and appliances as well. And then the kind of the upstream side is being looked at in kind of separate projects to Hy4Heat. So what was the objective? So the objective was to conduct kind of a generic safety assessment, looking at the risks inside of properties. And we were aiming to determine whether the risks of conveying hydrogen can be managed such that they're no greater than the accepted risk level associated with natural gas. So there's kind of a current risk level that, you know, the general public accept to gain the kind of the benefits of using gas. So what we're trying to determine really is that the risk from hydrogen aren't any greater than that, rather than using kind of like an ALARP approach, for instance, where you may actually end up with an increase in risk kind of inadvertently. And then also looking at providing recommendations and kind of appropriate engagement with the HSE just to ensure that there was support and recognition of the assessment. So the property types that are kind of covered by the assessment include most typical kind of residential properties, so terraced, semi-detached and detached, smaller commercial properties up to kind of 100 kilowatts gas usage, 2 stories and fed with the maximum operating pressure of 75 millibar. What it doesn't include is industrial facilities, which are kind of covered under different regulations, house and multiple occupation, so kind of like blocks of flats, again, which would have their own challenges, and buildings with kind of mechanical ventilation systems as well would be excluded. So what was the overall approach that we took? So this is kind of illustrating kind of all of the different inputs that went into the safety assessment. So on the kind of the top there is all of the data that we looked at. So this is kind of what Paul was speaking about before. So it's using the data that we collected from the GDNOs in particular to feed into the assessment, alongside all of the experimental data that was collected as part of Hy4Heat as well. So you've heard about kind of the leak testing that Steer Energy did, and also the dispersion testing that was done by DMV. What I don't think has been mentioned is the ignition testing that was also undertaken. So DMV did a number of experiments looking at ignition probability with kind of different typical domestic appliances, so things like toasters, washing machines, irons, and looking at how what the difference were in terms of igniting methane air mixtures and hydrogen air mixtures, just to inform the kind of the ignition probability assessment within the QRA. So that kind of this kind of middle bit here in like the red box is the QRA part of the assessment. So it's just stepping through, see the leak, the initiating leak, which kind of Paul spoke about, through to the dispersion assessment, which you heard from Georgina, then the ignition and consequences, and then looking at kind of what mitigation measures can we put in place to reduce that risk if we need to. So just kind of, this is a very simplified look at what QRA is. So we start off by defining our scenarios. So in terms of what leak causes are we going to look at and what leak sizes, and then we do a kind of a consequence and a frequency assessment for each of those in order to determine what the total risk is for those scenarios. So Sam's already spoke about kind of the consequence assessment side of stuff. So just kind of quickly on the frequency assessment. So the approach that we took was a combination of fault trees and event trees to kind of come up with the probabilities for each of those scenarios. And this is just kind of like a diagrammatic kind of version of what an event tree might look like. So kind of you start off on the left with your leak frequency. So this was the stuff that we got from the GDNO data collection, combined with kind of like the Steer Energy leak magnitude data. And then once you've got that, you look at detection and isolation. So do people smell the gas? And if they do they take appropriate action? So do they open their windows and doors to ventilate the space? If they know about the emergency control valve, do they close that off to stop the flow of gas, the leak? So we looked at things to develop kind of probability for that. We looked at things like the FCO data again, and the GSMR data as well. And then you move on to kind of looking at ignition and build up to flammable atmosphere. So do you get ignition at the source of the leak? That's quite unlikely, just given you would need to have a spark right at the kind of the location of the leak. And then, so if you don't have an ignition at the source, then you might build up to a flammable atmosphere, which is where we look at the kind of the dispersion data and dispersion modelling that was undertaken to build up to kind of a flammable atmosphere. And then if you do get there, that's when you look at just did it ignite or not. So again, that's using the kind of the data that we got from the DMV ignition probability experiments, just to inform that kind of ignition probability. And then once you've got those probabilities, that's combined with the consequence modelling that was undertaken by Sam. So what was the outcome of the assessment? So the outcome was that the risks were determined to be managed, that they can be managed such that they're no greater than the current acceptable risk level, as long as you have the use of appropriate safety measures in place. So we developed something called a safety annex that summarises these kind of recommended safety measures. And the purpose of this annex really is to support any site-specific safety cases that would have to be prepared by the GDNOs if they were to do any kind of gas community trials. So the annex covers kind of a collection of recommended risk reduction measures, which can be applied kind of across the board as a baseline for any kind of community trial. So what were some of those recommendations? So the key one, which I think we've already heard about, is excess flow valves. So the idea is to install 2 of these in order to limit the maximum flow rate. So there'll be a mechanical excess flow valve kind of upstream of the meter point, and then the new kind of hydrogen gas meter would contain an integrated excess flow valve as well, just to kind of increase the reliability of those valves. So what you're really looking to do with those is to limit the consequence of a really large leak into the property. So the next one is that all appliances and meters must be new. So this ensures that they're appropriate for use with hydrogen and also brings them up to kind of current standards. So for instance, appliances would have to have a flame failure device installed. So this would stop things like leaks from hobs being left on and gas cookers being left on. So hydrogen gas meters should also be installed outside of the property where possible. So it's important to note that we're kind of looking at recommendations for community trials at the moment. So if there are kind of situations where the meter can't be installed outside for kind of logistical reasons, then you would just need to do an appropriate risk assessment for the purpose of a trial. I think that would be possible kind of in those properties that, you know, if it can't be installed outside for whatever reason. And then the next one is sufficient ventilation in rooms containing gas appliances or substantial pipework. So this kind of goes back to Georgina's presentation on the effect that ventilation has in terms of reducing the concentration of gas in a room. So what we're essentially looking at here is compliance with some of the building regulation documents, which kind of stipulate a minimum level of ventilation in properties. They're not kind of, those regulations haven't been designed to limit kind of gas concentration. They're you know, they're more to do with kind of mold growth and stuff like that, I think. But kind of fortunately, they line up with the type of vents that were tested. So the vent size that we'd be recommending is around 100 centimeters squared. Is that right? No, 10 centimeters squared, sorry. that kind of lines up quite nicely with what is in the building regulations. So the next couple of recommendations are that you would need the same odorant to be used with the same effectiveness as currently used for natural gas. So just to give that familiarity and continuity with people kind of knowing how to respond. Also having kind of visual inspection of your pipework, and kind of for larger commercial properties, the installation of an automatic isolation valve with suitable gas detection. So that's where you're kind of using more than like 20 meters cubed an hour, which will be covered by your EFVs. And then obviously you need kind of competent and trained engineers to do any change out. And then just quickly to touch on the review that we went through with the HSE. So it was kind of an intensive and robust process, involved a lot of kind of presentations, discussions, reports backwards and forwards. And I think this was really, really key just to getting that kind of support and recognition of the safety assessment and of the risk reduction measures that have been proposed, so that we can kind of be confident that they are appropriate and would be suitable for kind of managing and reducing the risks of any kind of community trial with hydrogen. So yeah, that's all I wanted to say really. So yeah, I'll hand back to you, Phil.
Thanks, Sophie. I'm now going to open the second panel discussion. We do have a little bit of time to run over if we need to. So rather than limit questions to the time, I would like to try and answer as many as possible. If we do run out of time, we will endeavour to get in touch with the people who've posed those questions, particularly for some of the more complex ones, and we'll make sure that we answer all of them in some fashion. There were a couple of questions early on. I'm going to hand over to Mark Crowther now to moderate the second panel session. Mark, do you want some support on spotting questions, or are you happy?
Yes, please. I would love some support on spotting questions. Okay. Yes,
well, if please. I pose the question then, and then you can moderate the discussion. How about
Absolutely that? Right. Yes.
Okay. Fantastic. Let me introduce Mark, who's just on the screen. There was a couple of questions on relative flame speed earlier on, and how that affects the consequence of igniting either methane or hydrogen clouds. And the first one was from Jay Turnbull. So while the energy of hydrogen is less than that of methane, the big difference is the flame speed. Therefore, hydrogen delivers all that energy in a shorter period of time compared to with methane. Does this mean that hydrogen will be more destructive? I'll throw that open for Mark to manage.
Sam, would you like, and well, can I say just a few words first? I mean, yes, the flame speed of hydrogen is at 30% concentration, much higher than natural gas, probably a factor of 10, maybe even a factor of 20. But it's quite difficult to get 30% concentration of hydrogen in a room. So it's not simply a matter of comparing the stoichiometric flame speeds. Remember, hydrogen, natural gas stoichiometry about 10%, hydrogen stoichiometry about 30%. To get 30% concentration in a room, you need a big leak. Sam, do you want to add anything to that?
Yeah, I think you're right there, Mark. I mean, also it's worth adding just because the even if you multiply by 10 the flame speed, and you multiply, that doesn't necessarily mean, or you even multiply the overpressure by a factor of 10, doesn't mean the consequences increases by a factor of 10. They're not linearly proportional. And that was something that we actually went to pains to prove during the work.
Because we know that many properties, much of the modelling comes from steel boxes with single vents, yeah. Whereas we know that in a real property, first of all, maybe if you've got a moderate concentration, first of all, the window goes, then the outside door goes, then the ceiling goes. So you get progressive relief. so you don't get the sort of overpressures that you'd expect, that you predict from experiments with a single vent in a steel box.
Thanks, Scott.
Yeah.
I think that's all we can spend time on that. I think hopefully that also answers Dee French's question, which was very similar. I'm going to move on to one in the chat to Nickel specifically. Any comments on comparison of rate of change of pressure for methane and hydrogen?
Maybe again I can answer that one. Because the flame speed of hydrogen is much, we've just said is 10 times that of methane, the increase in flame speed is quicker. But if you look at those drawings, and I think Nickel presented some of measured flame speed versus versus time, these are still well in the zone of deflagrations. They are still within the zone by which the building has time to fail in a progressive fashion. These are not detonations by any means. These are not like TNT explosions. These are deflagrations.
Nickel, do you want to add anything to that?
No, I think that's
Okay.
answers that.
Fine.
My point of view.
Moving on to the Q&A part then. First one then, how can we determine that adequate blast relief is present in new build dwellings, given that the drive to make homes more eco-friendly, which means triple glazing and insulation resulting in far less leakage rates, and builders now have to reach new building standards? Sophie, I think you mentioned building standards in your presentation. Mark, do you want to say a few words before handing over to Sophie?
Yeah, there's a bit of a complication here, because what the current building control talks about is that the property should not have extraneous ventilation. What you should have is controlled ventilation, and document F requires an air change as occupied of about 0.4 air changes per hour. If not, we know we get sick building syndromes. In offices you get headaches, and in homes you get mold growth, and generally become unhealthy places to live. So clearly you want to bring a very drafty Victorian house down to a reasonable air change per hour. But conversely, as exemplified by COVID, neither do we want to live in airtight boxes.
Okay. Sophie, did you want to add anything to that?
No, that covers it. Yeah.
Okay. Next question then. How can you, this one's probably for Sam, because it seems specific to the number of occupants in a dwelling. How can you state an occupancy of 1.69 per dwelling, given that in 2020 the population in the UK was 68 million, with only 15.3 million registered dwellings? And I will add to that stat the stat that you saw earlier of 24 million gas connections. So,
yeah, it's a very good question. So I mean that occupancy level of 1.69, that's taken from the 2017 Office of National Statistics occupancy level, I think, which is 2.9. Yeah, I think it's 2.9. I'll find it and put it on the chat. But the point here is that sort of 1.69 figure takes into account that the frequency which people are in and out their house, so it's taking again, there's a lot of assumptions there. It is in the report, the assumptions that I base it on, but I think the bottom line is that it's the same for both methane and hydrogen. And we did again a sensitivity study to say, well, what happens if this occupancy level doubles or triples? And the output is that the consequences change by the same proportion for both hydrogen and methane. So I think so if you're comparing both the two gases, in terms of, is one more, how does one compare to another in terms of percentage? It wouldn't change, but maybe if you were comparing them in actual figures, in terms of maybe number of injuries, then yes, it would have an input there.
Okay, thanks for that. Another one from Mr. Turnbull. I think it's Mr. It's difficult to tell with a J. Could be Mrs. or even Miss. Previously, this is very similar to the previous question, but I'll ask it anyway in case there's any difference in opinion. Previously, we know that windows can be considered as explosion relief points. However, does your modelling take this into account? I guess that's directed towards you, Sam. And does it consider the effect of double glazing with normal glass and with toughened glass? My own interest is I live in a house with triple glazing, and I doubt you take that into account.
Yeah, that's true. So, I mean, if we look at some of the, look at some of the two pictures that I showed in that example, you can actually see that in two cases, and Mark, you can come in here if you agree with me, is that when it comes to glazing, when it comes to double glazing often just pops out the frame because the seal or the joint between the frame and the brick or the brickwork fails.
The screws come out.
Yeah, exactly. Whereas for sorry, someone's trying to get me to join another call. So whereas for single glazing, we found, in fact, Mark, this is the single glazing was what was used in the fib tests, the test that you did, and that fails and shatters, and you get glass throw. So actually, it's almost, when it comes to bent relief, yes, I suppose triple glazing will increase the overpressure inside temporarily until you have pressure release. But for the high concentrations of hydrogen, actually the phenomenon, the part that dominates in deciding overpressure is post vent failure. Mark, do you have anything to say on that?
No, absolutely. And the chances are that the back door's gone or the ceiling's gone. Yeah. There's something else gone before. I mean, yes, if the window doesn't fail, something else will fail, or you'll go into the hall or something.
Yes. Yeah.
Okay, thanks. There's a really useful question from Mark Howard here, actually, towards Sophie, but others please contribute if you. Do you see the safety annex recommendations being the default for all properties, or are these just for community trials? And I would probably expand that to say, what's the difference between the recommendations made in the reports and the QRA versus what one would need to do for a specific community trial risk assessment?
Yeah, so I think
if you answer that one first, Mark, and then you can.
Sorry, Mark. So I think it's the recommendations that we've set out at the minute are specifically for community trials. And the reason we've made that distinction is that we've been more conservative within this assessment. So, kind of as you gather kind of more information, as you go through and do community trials and gather more information as you're doing them, there's an expectation there that you may be able to reduce that conservatism as you find out more and more about, how hydrogen kind of interacts with the system in kind of the real world. Conversely, obviously, we could be wrong and it could go worse, but I don't think that's how it would what would happen. That's really why we've made that distinction around community trials. I think there's recommendations in there that would stay beyond community trials and be appropriate for kind of a full conversion, and there's some in there that may be too conservative and that you might want to look to take out. But I guess the point is at the minute that we don't have the evidence to say one way or the other. I don't know if you would agree with that, Mark, or add anything further.
Absolutely, because the dichotomy is this has got to be a safe trial, not a trial of safety. So there's not going to be very many data points, but we're really at a stage now following the Hy4Heat Annex. We have to go and try things, go and do things and look and see what the results are. And that's really the only way of doing it. We have to, we're not going to be able to wrap towels around our heads and solve this by thinking about it.
Okay, thanks. Related to that, there's another question from Navdeep Singh. A safety annex would be more useful from the perspective of rollout rather than from an isolated community trial. Is there a plan for Hy4Heat to provide conclusions or recommendations from a wider rollout perspective? I guess
not until we've actually done those trials. That's what we need to get on with the Hy4Heat project, with some of the village trials. We need to start learning by doing.
Okay, thanks. And one final question from Philip James. I'm trying to interpret quite a long question, which I probably don't have time to read out now, but I think your interest is in understanding the sensor rates for potential hydrogen sensors in ceilings. I know we have CO detectors currently. There is some discussion about whether we should have hydrogen sensors for to detect unburnt gas. The current plan is not to have those because odorant is considered a more effective form of protection. But I think your question was relating to what would the standards say was necessary for trigger rates for those alarms and sensors. Now, to some extent, you could argue, well, if we're not having them, it doesn't matter. But if we are having them, perhaps the panel could comment. And you mentioned a limit of 4,100 ppm, which equates to 4%.
Well, I mean, odorization has been shown around the world to be the best, to be currently, I think, state-of-the-art method of detecting gas leaks. Now, Japan, very, very low accident rates. Here in the UK, only 4 only 4 injury incidents last year and things. Very difficult to start recommending other sort of mechanical devices with their inherent levels of unreliability when most people's noses work pretty well most of the time.
Okay, thank you. There's no more questions, actually. There's one statement that somebody doesn't agree with our findings. That's entirely your right. Hang on, one last minute one from Navdeep Singh. Has the trial been approved by the HSE? If so, do we know when and where this will take place? There are no trials being approved. The HSE has written a letter of non-objection to which is as strong as an endorsement as you'll ever get from the HSE. But that's a letter of non-objection to the results of the work that's been presented this morning. The next step for community trials would be for those leading those trials to do specific risk assessments on the properties involved and the situations that those properties are in. And they would, in order to do that, they would need to apply the principles that are laid out in the assessment, the comparative risk assessment that's been made and presented this morning. I think that's it. Thank you for your time and for your questions and your interest. This is obviously not the end of the story, but hopefully it's been a good introduction to months of work that's been done. And if you want to know more, please go back to the link that's in the beginning of the chat and download the reports. Thank you then. I call this session to a close.
Thanks, Phil.